Hi, everybody. All right, let me share my screen. All right. So, are there any questions before we get started? Okay. Couple announcements. I wrote these in the Canvas too, but I added a few more presentation topics for class and office hours next week. For those that haven't done one yet, you can think about if you want to do the one next week. I can add some more for the week after Thanksgiving as well. In case next week's schedule doesn't work out for those who haven't done one yet. And the other announcement is no office hours today. Sorry, I have to. Something's come up. I have to leave right after class. And I just posted some new homework, but for next week. So if there are no questions, let's get started. So last time we stated the following theorem. Willbeck differentiation theorem. Which is the following. If I have an L1 function on RD, then so this is a solution to the averaging problem. Then the limit as the measure of balls tends to 0 over all balls containing a point x of 1 over the measure of b integral over b f of y dy is equal to f of x for almost every x. So this is the Willbeck differentiation theorem. And in particular, it solves the question regarding the fundamental theorem of calculus that we stated at the beginning of last class, if we apply this in one dimension. Okay, so the proof, the key ingredient in the proof are the maximal function estimates that we proved last time, the weak L1 maximal function estimate. So it's sufficient to show that the measure show the following. Let me write it like this. Let E alpha to be equal to the set of all x such that the lim sup over the measures of balls tending to 0, balls containing x of 1 over measure of b integral, so absolute value of integral f of y minus f of x dy. The set of all x for which this is bigger than 2 alpha. It suffices to show then the measure of E alpha is equal to 0. So it suffices to show that this set has measure 0 for every alpha bigger than 0. Right. Because then if we show this, take alpha to be a sequence 1 over n and let e to be equal to the union from n equals 1 to infinity of e to the 1 over, sorry, e1 over n. This is a countable, this would be a countable collection of sets of measure 0. The measure of e would then be equal to 0, which implies that, let's call this star, implies star holds on E complement, which is, in other words, almost every X in RD. Okay, so the goal is to show that this set has measure 0 for any fixed alpha. So that's a crucial point. We can fix this in the setup. So now fix any alpha bigger than 0. And we're going to try and prove a qualitative statement about this set, namely that its measure is equal to 0. Our bounds might depend on alpha, but as long as, right, so, but that's okay. Okay, so fix any alpha bigger than 0. Now, let f be an L1 function. F is an L1. For any epsilon bigger than 0, we can find G continuous, compactly supported in RD using the density of such functions in L1 such that f minus G in L1 of RD is less than epsilon. So find just a continuous function G that's close in L1 to F. Then the statement that we're after holds for G because it's a continuous function, right? Then the limit as this is equal to G of X for every X in RD, right? Because G is a continuous function. All right, now we're just gonna add and subtract G to the object we're interested in. So 1 over the measure, take a ball B, integral over B of f of y dy minus f of x. So B is a ball containing x. This is just equal to 1 over the measure of B, integral f of y minus g of y dy plus 1 over measure of B, integral over B, g of y minus g of x dy plus g of x minus f of x. All right, so I just added and subtracted integral over b of g of y and then g of x. I added and subtracted both those objects, and I have 3 terms now. Now, this is less than or equal to the maximal function of f minus g of x, right, which is a sup over all such balls for the first term, plus, well, let me write it this way. Let me rephrase this. So 1, this thing goes to 0 as a measure of B goes to 0, right? And so if we take such a limit, so this means that the limit as a measure B goes to 0 of 1 over measure B, integral over B, f of y dy minus f of x. Since this term tends to 0 as the measure of b goes to 0, we're left with just the limit over this term plus the limit over this term. Right? So this is just less than, this has nothing to do with b, right? So this is less than or equal to the first term we bound above by the maximal function, right? We bound this limit by the soup over these balls and putting absolute values on the inside. So this is less than or equal to maximal function f of f minus g star of x, and then plus f minus g of x, just the last difference. Okay, so that now we've obtained this bound. Right, okay, so now let's go back to this set E alpha. So E alpha is the set for which this thing is bigger than 2 alpha. Right? The set for which this limit is bigger than 2 alpha. And now I've bounded this set above by the sum of 2 terms. So I'm gonna devise write 2 different sets. I'm gonna call F alpha to be the set for which this thing is bigger than alpha, and G alpha the set for which this thing is bigger than alpha. The set of Lx for which this thing is bigger than alpha. So F alpha is the set of all x such that the maximal function f minus g of x is bigger than alpha. And G alpha is a set of all x such that f minus g of x, just the function itself, is bigger than alpha. And note E alpha, the set I'm interested in, is inside the union of F alpha union G alpha. It's a subset of this. Because if this thing, this object is bigger than 2 alpha, then at least one of these two has to be bigger than alpha, right? If they're both less than alpha, then there's no way that this thing can be bigger than alpha, right? So anytime we're in E alpha, at least you have to be in either F alpha or G alpha, which means you're in the union. So this is a subset of these 2 sets.
Quick question.
Yeah.
Do you want absolute values around the f minus g in the second term?
Probably, yeah.
Okay.
Yeah, probably. Thanks, Mike.
Sure.
Maybe let me fix this. Yeah, for sure. F of x minus g of x in absolute value is bigger than alpha. Yeah. I don't want to care about the sign there. And the maximal function, of course, is positive, or rather non-negative. Okay, so that's good. But then the measure, now I can compute the measures of these sets. The measure of G alpha, I can compute its size by Chebyshev's inequality. Remember, the measure of G alpha is less than or equal to 1 over alpha times the L1 norm of F minus G over all of RD. This is by Chebyshev. Which we proved last time. So that's good because this thing I can make small independent of alpha, right? At the outside I said this is smaller than epsilon, where epsilon is some arbitrary number, and alpha is fixed. And then the key point here, the measure of of alpha is less than or equal to some constant a over alpha times f minus g L1 of RD, also by the maximal function, by the weak L1. Maximal function bound. So this is the key technical element of the proof. The thing we had to fight hard to prove was the maximal function estimate, and that gives us this type of bound. Therefore, the measure of E alpha is less than or equal to, well, it's by subadditivity, it's less than or equal to the measure of G alpha plus the measure of F alpha, because it's a subset. So it's less than or equal to 1 over alpha times epsilon plus A over alpha times epsilon. Alpha is fixed, right? This is the key point of the proof. Alpha is fixed. And now I can take epsilon to be as small as I like, right? Which is fixed, and epsilon bigger than 0 is arbitrary. Okay, so that completes the proof. And I just wanted to highlight one thing that we kind of use over and over. But okay, see at the end we have this bound which looks bad. It looks bad, right? If I didn't set things up correctly, because I have alpha, which I think might be a very small number. I have epsilon here, but the point is I was able to fix alpha first and then choose epsilon small later. So the order of constants of fixing small constants matters, right? And why was I able to fix alpha at the outset? Well, it's because of this observation, right? This very first step in the proof, I said it was sufficient to prove that the measure of this E alpha is equal to 0 for each fixed alpha, because I could take a countable union of such sets and know that if each one has measure 0, then the countable union still has measure 0. So like we had to work hard to and when we developed a Lebesgue measure to prove like the additivity properties of the measure under even for infinite quantities, like or countably infinite quantities. And we use this all the time. Like we use this here, right? In saying that if I know that each of these sets has measure 0, then the measure of E has to be 0 too. So that's just one that allows us to pick the constants in a good order in this proof. And we use this. We've used this almost like every day since we've been doing these more refined properties of Lebesgue integral. Okay, so any questions about the proof or comments about the proof? Questions, comments? Sync the file. Okay, a couple remarks. One is that, as Andy suggested last time, this type of theorem doesn't really care too much about the global integrability of f, but rather the integrability of f on say a ball of radius 1, say around a point x. So local integrability we say f is in L1 log of RD if f of x times chi b of x is integrable for all balls B in RD. So if your integral over each ball, over each fixed ball, then we say you're locally integrable. So what this is saying is we don't care. This is like saying that f is a nice function, and we just don't care about okay, so integrable functions, it matters how fast they decay as x goes to infinity, right? We need some good decay. We already saw that if you have to decay kind of better than 1 over x to the absolute x to the d, in order to lie in L1. But not so if you want to be in L1 loc. So it's just so in particular, functions like the book gives two nice examples. E to the x is in L1 loc, right? This thing grows crazy to infinity, but once I fix a ball, that you can integrate this function over a ball, right? X to the minus alpha for alpha less than d, L1 loc. Right, because this function that has a problem at 0, but I've made the problem benign enough so it's integrable at 0. It doesn't have enough decay at infinity to be integrable, but that's okay. I just care about its integrability on some fixed ball, right? So these functions are L1 loc. So the differentiation theorem holds for f in L1 loc. So I can change the hypothesis here. So if the function is an L1 loc of Rd, then this limit is equal to f of x for almost every x as well. So that's just a small remark.
Is every function that's finite almost everywhere locally integrable?
No. Sorry, I'm getting some feedback. No, right? Because just if I took, so an example would be x to the minus d plus 1 is not an L1 loc. Where this function's infinite only at the point x equals 0, right? Or would be infinite only at the point x equals 0. But the point is it grows too fast near x equals 0. So it's a matter of rate of growth around like. So what L1 loc does is it doesn't care about the behavior of function at infinity, but it does care about the behavior of the function, how fast it grows around any fixed point. So I mean, not just this function, but like x minus p to the minus d. Sorry, this I want to put parentheses over this. Sorry, minus d. Like this is not an L1 loc because it has a bad singularity at x equals p. So yeah, the local integrability is more just like just not caring about the behavior at infinity, but we still have to care about how bad the singularities are for the function, how bad its singularity is.
Can I go further, being annoying, and ask about the relation between L1 loc and L infinity?
L1 loc and L infinity. Sorry, can you repeat the question? I didn't quite hear that.
So are there any relation between L1 loc and L infinity?
I mean,
whether
like
one is included in another?
Included in the other. So from this example, right? You see that that we cannot have L1 loc does not sit inside L infinity, right? from this example. But the opposite inclusion is true, right? So L infinity is inside L1 lock, right? Because if f is in L infinity, this means that the soup the L infinity norm, which is the soup of f is finite, right? And then if I integrate f over any ball, absolute f over any ball, then this is less than or equal to the measure of the ball times the L infinity norm of f. So this means that L infinity sits inside of L1 lock. Yeah. Yeah, so that's that's there's some comments about the theorem.
Can I ask one more question?
Yes.
Do we know, or is it true that the continuous functions with finite measure support are dense in L1 lock?
They're dense in they're dense in L1. Sorry. So okay. So the question is C inside of dense in L1 lock. So the compact support thing might be tricky. So okay, so all right, so the I guess the appropriate norm. So it's L1, like local L1 is not maybe super useful for such things, right? Because what's a good norm? What's a good L1? What's a good norm for L1 lock?
Yeah, it doesn't really see that.
Right? Does that make sense? Like, because like for take this function for example, in like what would be like a candidate for a norm would be like you want to take supremum over the ball over the integrals over balls or something like that, right?
Yeah.
But that's clearly infinite.
Which obviously can.
Yeah, right. It's obvious. It's clearly infinite for objects like this. So it's not super useful to think of this by itself as a metric space, for example, because a lot of the elements that there's no real natural L1 lock norm somehow, right?
Okay, so the proof that we just did kind of relies on finding some G, right, that is close to F under the L1 norm.
Yeah. But we could, but what we could do is just pick our. So we'd have to adjust this a bit. What we could do is just fix a ball, say of radius 1, containing. Remember at the end, we're only care about so we just need to be we just need to be a bit careful about how we go about the order of things. So since we only eventually care about we're picking an x and letting the measure of the balls around x going to 0, like just at the outset we could just say fix a ball of some radius centered at x, and then work strictly on that ball. And then we could approximate f by a continuous function on that ball, on that big on some big ambient ball, right? And then do everything inside. So yeah, you can just use the L1 norm on a fixed ball of radius capital R that we fix at the outset, say, or radius 1 if we like.
Okay. That passes the smell test for me.
Okay.
Is it not a problem that the maximal function is overall balls of any size?
So the maximal function estimate. Sorry.
And we can move on. I'm sorry, we don't have to spend time on this.
Sorry, I'm trying to see if I can understand the questions in the chat as well. They're the same questions being asked in the chat. I'm just
Oh, I see.
Yeah. So how do we replace the maximal function? Sorry, is this not not clear? We could say at the outset, let's only study we're trying to prove the Lebesgue differentiation theorem. Let's fix a ball of radius. Let's cover RD with balls of radius 1 or radius 12 or something like that, centered at all the integers. All the rational or all the rational elements of RD with rational elements or something like that, or integer elements. Fix one of those balls, and then take your f and L1 look, and then now just set it equal to be 0 outside the ball. Like just take your function, set it to be 0 out, replace f with f, and then something that's just 0 outside the ball of radius 1 or whatever size ball you fix at the outset, or radius 2. Now you move from having an L1 log function to a new function which is L1, right? And then now just carry out the rest of the proof for this new L1 function.
Got it.
So does that make sense? It's just that ultimately the property that we care about is local. So it's a property about what happens to f of x near x, right? So we could just at the beginning we could just take your L1 log function, just cut it off to be 0 outside of a big enough ball around the point x, and then proceed from there.
Perfect. That makes sense now. Thank you.
And let me see if I've answered also answered the chat. Okay, Samuel, I see you had questions, and I'm not sure if I answered any of them. Is that correct, or is this?
I mean, I just try search L1 log, and then it says it actually has a metric, because we can kind of add countably many infinite metrics and form a new metric in some very sophisticated way. But then, I mean,
so then you have to ask yourself what, like, so there's abstract properties of spaces. Yes, okay, it's metrizable as a topological space or whatever. But like, you have to ask yourself what are we doing with such a metric?
Yeah, I mean, I can't see any intuition behind that.
Exactly. Yeah. Yeah. So like for these type of, so with this type of question, um, uh, it's almost best to just stick with the first question you're interested in. So if we decide we're interested in this theorem, and so the only observation, like, rather than get hung up on what L1 look is as a metric space, it's just more like what are the assumptions we want about F for which so that this theorem holds. And then like the notion of L1 loc is useful in that sense. And local spaces are useful in many other senses, but oftentimes in that context where it's like in this I have something I'm interested in. What properties of the space do I need? If the question is, do I need a metric if I want to show space is metrizable for some other reason, then that metric might be useful. But does this make sense? Like,
Yeah.
it's quickly you can get into an abstract discussion where where you lose a little bit of sight of what you're interested in the first place. But these are good questions to ask, yeah. But like metrizable is like oftentimes when you have to ask the question, is this can I put a metric on such a space, and it's difficult to answer, then you better really care about the metric, or about the existence of a metric, right? Does that make sense?
Yeah.
All right.
I see. Thanks.
Great questions, guys. I'm not to say that these like local LP or L1 spaces are not super useful. They come up all the time, actually, in practice. As you can see, like these are not crazy functions, right? So they. Okay, so where were we? Okay, so a couple of applications of what we've done. One is the notion of Lebesgue density. Is a definition. If E is measurable, X is an RD. We say X is a point of Lebesgue density of E if the limit over measure balls tending to 0, balls containing X of the measure of B intersect E divided by the measure of B is equal to 1. So what does this mean? It means that as long as I take the ball around X to be small enough, then E mostly covers it, right? Small enough balls around X are nearly covered by E. Right? If it weren't so, if E was so so sparse around X, then once I intersect it with a ball, which is a ball of some radius around X, I'd expect this set to be smaller than the measure of the ball. Right? I would be missing a lot of points. But those points, so that can certainly happen for a measurable set, but we'll call X density points of E. So this is what the definition is: a density point of E if this limit is equal to 1. So another characterization. So X is a point of Lebesgue density of E implies that for every alpha less than 1, close to 1, for every alpha less than 1, and every small enough ball, the measure this holds. So E covers a large portion of a large fraction of B. And then a corollary of the theorem that we just proved. So a corollary of theorem, of the Lebesgue differentiation theorem, is that if I have a measurable set E, you can ask which points are the points of Lebesgue density, or how many of them are. Then one, almost every X in E is a point of Lebesgue density. And 2, almost every X not in E is not a point of Lebesgue density. And the proof, I'll sync the file. The proof is just the theorem. So apply the theorem to f of x is that just a characteristic function of E. This is just equal to the measure of E intersect B divided by measure of B. Right? Okay.
Can I ask a quick question about Lebesgue density?
Yeah.
I might be a little confused. So is the analogy like an interior point? Like what if you have like a surface in like R3 or something, then a small ball around it is not really, for any point in E, the surface, a ball is like mostly not covered by E.
But okay, that E has measure 0, right?
Oh, okay.
It's such an E would have measure 0, right? Inside of R3.
Right.
So yeah, sets of of lower dimension aren't going to be they're not going to have Lebesgue points. So yeah, so this is really about like so that helpful that example helpful then. Yeah. Yeah. So it's one application.
Just as a follow-up on Andy's question.
Yeah.
Are you saying that in that case, E has measure 0, which means like part 1 of that, the corollary is just like vacuous?
Yeah, right.
So like almost every of almost no points.
Yeah, exactly. Yeah.
Okay.
Yeah. Because because this thing on the numerator is just identically equal to 0, right? If you take a measure 0 set and intersect it with anything you like, you still get a measure 0 set, right? Because,
okay.
Yeah. So the points. So this definition sort of has content only if like E is measurable with positive measure, right? Too. Yeah, but I think this word density is meaningful here. Like it's a point that there's a lot of stuff in E around that point. Is what it means. It's kind of okay. so that notion comes up sometimes. So another notion that comes up that we'll make a little bit more use of is what's called the Lebesgue set. So we're just going to define this. It's almost like it's a slightly smaller set than the set for which the previous theorem holds. So given f, say an L1 loc of Rd, the Lebesgue set of f I think it's often called is all points x bar and Rd such that one f of x bar is finite, and two, the limit as the measures of balls tend to 0, balls containing x bar absolute value, this is equal to 0. So two observations. Observation, maybe I'll call this I and 2i. Observation 1 is that if f is continuous at x bar, then x bar is in the Lebesgue set. All right, this holds at points of continuity. This Lebesgue set contains all points of continuity. And two, if it's in the Lebesgue set, then the positive part of the Lebesgue differentiation theorem holds. It's one of the almost every collection of points for which the Lebesgue differentiation theorem holds. If x bar is in the Lebesgue set of f, then the limit is equal to f of x. All right, so the conclusions of the Lebesgue differentiation theorem hold for the points in the Lebesgue set. Okay, so we can ask then, since it's a stricter criteria, right? Then being in the Lebesgue set implies that this holds, right? In the previous theorem, we showed that this held almost everywhere. But since this is a stricter set of conditions, we can also ask if the Lebesgue set, if almost every point is in the Lebesgue set, and that's true as well, but we need to prove it. So it'll essentially be a consequence of the previous theorem. So actually, sorry, let me state the result. The corollary again to the theorem is that if f is in L1 loc of Rd, then almost every x in Rd is in the Lebesgue set of f. Okay, so almost every points are in the Lebesgue set. And we'll again just apply the Lebesgue differentiation theorem, but with a bit of a trick. So we apply the Lebesgue differentiation theorem. And if you look back at this at the statement here, we can't. There's nothing since we've put absolute values inside already. It's not quite clear what we apply to the theorem to, right? Because f appears in a weird way. F of x bar appears in a weird way inside here. So the trick is we're going to just approximate this by rational numbers. So we'll apply the differentiation theorem to the function f of y minus r for r and q. Okay, so this is just a trick, and then we're going to approximate each f of x bar by points y and q, points r and q. This is frozen. Okay. So what does the theorem say for this? There exists so there exists a set for every r and q. There exists a set ER with the measure of ER is equal to 0. It's a collection of points for which the Lebesgue differentiation theorem fails, such that the limit as the measures of ball tend to 0 for balls containing x of 1 over measure of ball f of y minus r dy equals f of x minus r for every x that's not an ER. So right, this Lebesgue differentiation theorem holds almost everywhere. So so this limit holds. You can find a set of measure 0 for which this conclusion holds on the complement of that set. Measure 0. And then E, if I let E to be the union, right? Again, we're using this countable subadditivity. If E is equal to the union of the ERs, then the measure of E is equal to 0. And so now just let x bar be not an E. So E is so it's an E complement. Then and a point for which f of x is finite, right? If you're integral function, you're finite almost everywhere, right? Sorry, I'm not sure what's wrong with my iPad. This is finite. And then given epsilon 0, there exists an R and Q such that f of x bar minus R is less than epsilon. And then integral over b f of y minus f of x bar. The thing we're interested in is less than or equal to 1 over the measure of b integral over b of f of y minus r plus plus just f of x bar minus r in absolute value. And then this is small, and this we know tends to 0 as the measure of b tends to 0. So therefore, the lim sup as the measures. F of y this is less than or equal to 2 epsilon. Which means that x bar is in the Lebesgue set. All right, and so this is so this means as long as you're finite now, you're in the Lebesgue set, and you're not. So as long as you're not an E, the set of measure 0, which you had to throw out, and you're finite, then you're in the Lebesgue set. So this set has measure 0, and then we know that f is finite almost everywhere. So then therefore we've got almost every x in RD, x bar in RD. Any questions about the Lebesgue set? Okay. So now that we have this notion, we can come back to the notions of good kernels and approximate identities. So convolution with a kernel. So f k delta, we'll call this, of x is defined to be integral over Rd of f of x minus y k delta of y dy. And in the beginning of class, we defined the notion of a good kernel, which was as follows. So we had 1, that the integral of k delta was equal to 1. 2, that k delta was the integral of k delta was bounded, uniformly bounded for every delta bigger than 0. And 3, here we're going to think of delta tending to 0. Last time we indexed these by integers capital N, with n tending to infinity often, but here we're going to replace n tending to infinity with delta tending to 0. And 3, we said that for every eta bigger than 0, integral tends to 0 as delta goes to 0. So this is our notion of good kernel before, and we proved if f is continuous at x, then k delta convolved with f of x tends to f of x as delta tends to 0. Okay, so this is what we showed towards the beginning of class, that at points of continuity, good kernels behaved like almost like the identity function in the limit. Okay, so what the goal that we're after now is we're going to we'd like to relax this hypothesis that f is continuous, that this holds at continuous points of continuity, and we're going to replace the notion of points of continuity with the weaker notion or of the points in the Lebesgue set of the function. All right. However, in order to get the conclusion that we're after, this type of conclusion for points in the Lebesgue set, we're going to need to strengthen the notion of the admissible class of kernels that the requirements on the kernels we allow. All right. So we're going to define so last time I said I used the words good kernel and approximate identity interchangeably. Stein and Shikarchi are careful that they use good kernel for kernels like this, and then they call the following class of kernels approximations to the identity. So definition, this is called an approximate identity. K delta as above is an approximate identity if one, it's integrable over RD. Two, rather than a bound on, so instead of 2 and 3 from above, maybe I'll call these 2 prime and 3 prime. So above, so one is that we're going to replace the global integrability bounds on bounds on its growth. This is less than or equal to some constant a times delta to the minus d for every delta bigger than 0. And 3 prime is that, so this is 2 is a global bound on the size of the function. It can't be bigger than delta to the minus d by some uniform constant. And 1 is that this is less than or equal to a times delta divided by x to the d plus 1 for every delta bigger than 0 for every x in RD. And 3 can actually be relaxed, or so this is some bound on the behavior of the function as we go to infinity. So basically, you want integrability outside of any ball of fixed radius. This is big. This is less than or equal to a times delta to the epsilon over x to the t epsilon. So for some fixed epsilon. So that would be a suitable replacement as well. Let me use a twirl here. If there exists a constant a bigger than 0 such that falling hold. So these are approximations to the identity. And the remark is that if 2 prime and 3 prime hold, then 2 and 3 hold above. So these are stronger assumptions. So it's harder to be an approximate identity than it is to be a good kernel. So remark 2 prime. I don't know why I put the primes on the outside. Plus 3 prime. Imply these two. So note, so how do we see this? Because we've proved that the integral over a ball, outside a ball of radius epsilon of dx x to the d plus 1, this is less than or equal to c over epsilon for some uniform constant. Therefore, integral over rd k delta x dx, this is equal to the integral x less than delta plus the integral of the same thing over for x bigger than or equal to delta. And this is then less than or equal to a, and the ball of radius delta, we use the bound 2 prime. And this ball has measured delta to the d, so that we just get a constant here, and then plus a times delta. Now we use 3 prime for the outer ball. And so this is less than constant times 1. So it's bounded. And then for 3, this implies 2. That the kernel is absolutely integrable, bounded, its integral is bounded uniformly in delta. And for the third property, if I want to just fix an eta and take all x bigger than or equal to eta, this quantity is less than or equal to, we just use the third bound, so a times delta integral x bigger than or equal to eta dx over x to the d plus 1, and we computed this integral. We know this is an a times delta divided by eta. Eta is fixed, and so this goes to 0 as delta goes to 0. So this implies 3. Okay. So some examples that we've seen from the beginning of class: Dn, the Dirichlet kernel; Fn, Fayet kernel; and Pr, the Poisson kernel. So Dirichlet, Fayet, and Poisson. These kernels are all, they all fall into the stronger, the more restrictive class of approximate identities. Here. R is delta. Okay, and the theorem that is now a consequence, basically a consequence of the differentiation theorem, is that if k delta is an approximate identity, and f is an L1 of Rd, then k delta convolved with f of x tends to f of x as delta goes to 0 for all x in the Lebesgue set of. So in particular almost everywhere. Okay. So that's the theorem. I think I'd like to do the proof next time. It's a little bit long to do in 10 minutes. So maybe stop the lecture now and ask if there are some questions or anything we want to discuss, especially since I have to miss office hours. Any questions?
So can I clarify 2 things?
Yeah.
The first thing is when we define good kernels, we work on the torus, but now we work on RD. Would there be any difference?
No. Before, so the proof that we what we proved before is for a good kernel like this with these assumptions. Yeah, we were working a torus, but if I make the same hypothesis for on RD under these assumptions, then I have this pointwise convergence at points of continuity. So under these assumptions, I can prove this result, points of continuity. To prove the convergence on the Lebesgue set, I need a little bit more control over the behavior of the kernel on right. I need a little more specific control on the behavior of the kernel to get to prove the analogous theorem on the Lebesgue set. So this is why I make this slight strengthening here.
I see. The second question has been asked by Joseph.
Yes, sorry. Um, excellent. Excellent point. Yes, the Dirichlet, our lives would have been very easy. The Dirichlet kernel. This is an example of a kernel. And I see in my notebook that I did this example examples in my when I wrote down my notebook. This appeared before I said the definition of good kernel, and it's sorry. Yes, the Dirichlet kernel is not a good kernel. Yeah. Thank you, Joseph.
Under what conditions is the Lebesgue set the same as the points of continuity?
So, okay, that's a good question. So remember how this is okay. So this is a subtle thing. So for many purposes, when we study an L1 function, for example, we think of L1 as an equivalence class of functions, right? And so there's no, but the Lebesgue set is actually representative dependent. So if I have two different functions, the same equivalence classes, the Lebesgue set is maybe different for these two classes of functions. So sorry. So what was your specific question? So you need to be a bit careful here because for I could just take a continuous representative, right? And something for many functions in L1, I could take a continuous representative, and then every point would be just in the Lebesgue set. Whereas there's another class, there's another element of its in the same equivalence class that has different Lebesgue set, right? Because I could just if I just like if I just took two functions that are a little bit different, then like this point won't be in the Lebesgue set, but it am I still sharing my screen? Yeah.
I guess maybe a follow-up question is like, is it possible for the Lebesgue set to differ from the points of continuity by a set of positive
measure? Yeah, I think so. Interesting. Yeah, I don't see why not. I don't see why not. That makes is that I'm not I don't have an example in mind, but I don't see why not. Yeah,
it works for me.
Yeah. Yeah, I'm not sure actually. I'm not sure, but I don't see I don't immediately see why not. Any other questions? Okay. If not, then I'll stop the share, sync the file, stop the share, and then see you guys on Tuesday. Please have a look at the presentation topics if you haven't done one, and you might want to do it if you're have some time next week to prepare for one. Okay. All right, everybody. See you next week.
Thanks.